Welcome everyone to this special episode of Know Your Scientist, brought to you by the Kshama Ahmedabad Academy of Sciences. Today, we are truly honored to host one of the most distinguished and influential voices in modern theoretical physics, Professor Rajesh Gopakumar, currently serving as the Director of International Center for Theoretical Sciences, ICTS-TIFR, Bengaluru. Professor Gopakumar is a world-renowned string theorist whose work spans across quantum field theory, holography, and topological string theory. He earned his PhD from Princeton University under the mentorship of Nobel Laureate Professor David Gross and has since charted a path of deep and original contributions to our understanding of the fundamental structure of the universe. Among his most celebrated achievements is the Gopakumar-Vafa duality, a profound result in the topological string theory developed in collaboration with Professor Gopakumar-Vafa. Over the years, he has built lasting collaborations with a wide circle of leading physicists both in India and abroad. From India, his close collaborators include Shiraz Minwala, TIFR, with whom he has worked extensively on large N-gauge theories and holography. His Indian collaborators are Aninda Sinha, Arjun Bakchi, Apratim Kaviraj, and Roji Pius. And internationally, he has collaborated with Gopakumar-Vafa Harvard, Robert Dijkgraaf from IS Amsterdam, Premier Institute, and all working at the frontiers of string theory and holography. These collaborations reflect not only his scientific depth, but also his role as a bridge builder in the global theoretical physics community. Now, in his 10th year as a director of ICTS, Professor Gopakumar has helped shape the institute into a thriving hub of interdisciplinary science and academic excellence, hosting some of the most vibrant scientific programs in the century and beyond. In today's conversation, we will explore his scientific journey, the promise and challenges of string theory, his vision for fundamental science in India, and his personal philosophy that has guided a remarkable career in research and leadership. Professor Gopakumar, thank you for joining us. We are delighted to have you here.
Welcome.
You did your MSc in physics from IIT Kanpur. I guess it was a 5-year integrated program, BSc plus MSc?
Correct.
Okay. Would you like to share a memory about it?
Oh, that was one of the best things I did, I think, in my life. Have the decision to join the MSc 5-year program at Kanpur. It was a very unique program. It has had a large number of very good physicists come through it, many seniors of mine, many people afterwards as well, and it continues to this day. One of the best things was also the fantastic teachers that we had in IIT Kanpur at that time. Also, some of the wonderful batchmates in physics that I had, with whom we have now decades-long friendship, so it was a very memorable and very formative part of my growth as a physicist.
That's great. These days, they take IIT JAM exams for that. Was it the same back then?
This was through the IIT JEE exam, because it was a 5-year program after class 12.
Okay,
so you did in fact, there was not a separate BSc. You just continued. You joined after class 12 and you continued for 5 years and got an MSc. Nowadays, I think they have a dual degree which you can do in 5 years, or you can do a bachelor's degree in 4 years, BS degree. So there is a different option now, but at that time it was a 5-year degree.
Okay. You appeared for JEE exam, as you said. So were you interested in a career in engineering?
No, I never was thinking of an engineering option. I only appeared in it so that I could try for this IIT Kanpur physics program. That was the only that program, and there was a similar one at Kharagpur in physics at that time. So these two were the ones that most interested me. Otherwise, I would have probably studied some other college my physics.
IIT Kanpur has produced, including you, some of the finest physicists of India. What was the environment or culture at IIT Kanpur that makes it so productive?
I think it was at least in my time, the teachers who were very dedicated, who gave their heart and soul into exposing us to the modern ideas of physics, and not only through their classroom lectures, which were often very inspiring, but also through conversations, informal interactions which we had over chai or at their house and so on. You got a very kind of very close feeling of mentorship, which I think was very important. And like I said, having some wonderful batchmates with whom I discussed physics and learned physics with, that was also very enriching.
You joined Professor David Gross for your PhD. So, what made you choose him?
So I, of course, had heard of David Gross as one of the very uh, uh, great mentors and teachers at Princeton, and that he had, of course, some stellar students in the past, and that so people told me when I consulted some of my senior colleagues in theoretical physics, many of them were very strongly suggesting that I try to work with David Gross if I had an opportunity. And also another reason was that it was at that time I was not sure I would really want to do string theory. I was more interested in quantum field theory and related things. I was a bit of a skeptic about string theory. And in fact, my PhD was really on quantum field theory. And David Gross was one of the major pioneers in the development of quantum field theory in the 70s and 80s. And it was therefore very appropriate to try to work with him. But I didn't want to close the doors on string theory. I also wanted to learn what it was like to get a better feeling, but I wasn't necessarily intending to work only on string theory. And it was interesting because at that time David Gross was working on a problem which was at the intersection of string theory and quantum field theory in terms of two-dimensional Yang-Mills theories. So it was very appropriate topic, I think, for me to start my PhD on.
Okay. Had he already received Nobel Prize by the time you were
No,
joining?
no, no, no. I joined him in 1992, 93, really. And he got his Nobel Prize only a decade later in 2004. That was much after my PhD. But of course, he had done the work for which he got the Nobel Prize and for which he was, of course, already well known for on asymptotic freedom. That had been done with his first PhD student, Frank Wilczek, in 1974. So that was already, of course, there a couple of decades before.
String theory is one of your main research interests. Could you explain what string theory is and why does it matter? In the simplest terms, we have school students and BSc students here as an audience.
Yeah, no, string theory is it's a multifaceted theory. I think it is. It's often, I think, somewhat misrepresented in the popular discourse, meaning people often either hype it up too much or they kind of criticize it too much. I think the truth is always somewhere in between. I think it is a very promising theory. It has some remarkable features which we have learned over the last several decades. But it's multifaceted in the sense that it is often viewed as a theory of quantum gravity, which it is in the sense that it gives us a consistent way to describe gravity, which is one of the fundamental forces of nature, at in a regime or in the when distances or energies are high enough that you have quantum effects very important. So, as you all know, quantum mechanics is at the foundation of reality, despite our not being able to see it at the in our everyday life in a direct way. It's far from our immediate experience, but quantum mechanics underlies the reality of atoms, which ultimately everything is made of. In some ways, it's many of the important properties of even light is quantum mechanical in nature. Quantum mechanics, and now quantum mechanics pervades all our technologies. But we understand how other fundamental forces of nature, like electricity and magnetism, are modified by the quantum effects. So we understand how Maxwell's equations, which we learned in school, how they are modified when we take into account quantum mechanical effects. But gravity, which we learn in school through Newton's laws, which of course got modified by Einstein in the general theory of relativity, which described gravity in terms of space and time, that the motion of objects in a gravitational field is really a motion in a curved space-time of, say, a planet going around the sun, is really to be thought of as the kind of simplest motion that that object can undergo in a curved space-time that is generated by the sun. We know Einstein's theory as a description of gravity at the classical level, but so that is very much like the Maxwell's description of electricity and magnetism. But we do not know how it is modified at the quantum level. And this is very important if we want to understand what is really at the heart of black holes, or at the heart of the Big Bang, at the very origin of the universe. So quantum effects in gravity need to be understood in a framework which is consistent mathematically. String theory provides one such framework, and in some ways probably the only reasonably complete framework that we have. So that's one facet of string theory. The other facet, which in a way is one that I have been working on a lot, is how strings actually arise even in the other interactions. For instance, you can say there is a precursor of strings in the pictures that we learn in electrodynamics also, where we talk about the lines of force.
Yeah.
So maybe I can use the blackboard um, and explain it through a picture.
Yes, sir.
So we often learn in school about two charges, and we draw these lines of force between the charges, right?
Yes,
so this you draw sometimes some magnetic lines,
yeah,
or sometimes some electric lines. So all these lines. So let's say this is a positive charge and that's a negative charge. You'll draw these lines of force emanating from the positive charge and coming to the negative charge. And this picture is in fact how Faraday viewed electromagnetism. And Maxwell actually initially tried to understand electromagnetism in terms of the dynamics of these lines of force, before he arrived at these Maxwell equations, which are really for the electric field. The electric field is an object. At any point you draw an electric field as a vector. So there can be an electric field. So it's basically the little bit tangent to this curve that the electric field describes. So you can have an electric field here, so on. And he wrote equations finally for them. But before that, he was actually looking for equations for these lines of flux. How do these lines move? And that didn't succeed in his case. So he couldn't make this Faraday's picture precise. But in the strong interactions, which are in the nucleus, when we are talking about the quarks in the nucleus, or in similar kind of in similar systems like mesons, which are really a quark and an anti-quark.
Yes.
It's the analog of a positive and a negative charge. Then the lines of flux are also there in the strong interactions, but the lines of flux are confined, exactly. So they are kind of bunched into a little tube like this. They cannot spread. Even if they try to go out, they're kind of pulled back and confined into a little narrow tube. And this tube is a highly concentrated amount of flux of the corresponding field, and it acts like a string. And you can actually experimentally, in some sense, see the signatures of the string. You can even do computer simulations of these quarks and antiquarks and see that the string has a tension. There is a tension associated with this string, because that's the characteristic of a string. It has some tension, and then it can vibrate and do things like that. And so in quantum chromodynamics, or QCD, which is the theory of the quarks and their forces, you do see emergence of these string-like objects. Okay. And here there is a much better chance to understand what the dynamics of the strings is. And in some remarkable developments of this gauge string duality of the last 25 years, we have begun to understand a little bit that the strings that describe the strong interactions, or theories very much similar to the strong interactions, now are really the kind of string theories that also describe gravitational interaction. Okay. So we have a very remarkable duality, what is called a gauge string duality, between these strings that really can appear in other situations as well.
So are these lines that we are talking about do represent electric field, because there are two quarks?
So it's the what is called the chromoelectric field. It is the analog of the electric field for the strong interactions. So the strong interactions are governed by QCD. It's a theory which is a generalization of Maxwell's theory, and it has electric fields and so on, which are a little more complicated compared to the electric fields of the charges. The quarks, of course, also have electric fields coming from the electrical charges, but those are much weaker than this strong force. So I'm not considering those electric fields. This is purely the chromoelectric field of the strong interactions.
The string that is made from this chromoelectric fields, and we study the properties about it, and then we use it for the gravitational waves, right?
For the understanding of quantum gravity, or we can view it the other way, that the gravity sometimes can give you an idea of how to describe these strings. Because the strong interactions, we don't have the same level of calculational ability that we have in electromagnetism. These are strongly interacting. That's why they're called strong interactions. So a lot of the information we know about the properties of nuclei or these mesons or other hadrons, other particles, are coming from computer simulations. So we don't have really a deep conceptual way to understand these from first principles, and maybe string theory can help to describe the strong interactions through the string as the fundamental object, by thinking of this as the fundamental object and various excitations of the strings as the different particles that you see in the strong interactions. So that's an aspect of string theory, I think, that people are not so familiar with, that string theory not only can enable us to study the strong interaction, study quantum gravity, but also things like the strong interaction.
Got it, sir. So as we talk about the strings between quarks and the strings that we study about in while studying gravitational waves, as you just mentioned and we just clarified it, are there differences in the properties between both of those strings because we are using one to understand another? So,
Yeah, that is the remarkable thing, that they are essentially the same kind of string.
okay.
Or I would rather say that this string, that one I was talking about
Quarks.
in terms of the flux lines,
Right.
is a kind of a shadow of the fundamental string, which really doesn't have any thickness.
Okay.
This string has a certain thickness associated to it, and the thickness, in a sense, comes because it is really a shadow of a fundamental string. A fundamental string has length but no thickness. And the shadow is this idea of holography that you mentioned in my work, was one of the themes and has been a dominant theme for 2 or 3 decades in string theory. The idea that theories of gravity are holographic, namely that you can describe the motion of strings or gravitational objects in certain spacetimes. At least we understand it in certain spacetimes very precisely, that it is the motion of these strings in those spacetimes describing gravity can be viewed in terms of their shadow on a boundary of that spacetime. And that is like one lower dimensional space. And it captures all the information about the higher dimensional space. So in that sense, it's a shadow from which you can reconstruct the higher dimensional space. So this string in the strong interactions can be viewed as some kind of a shadow of some effectively higher dimensional string.
Okay, sir. My next question is like, because it has its some kind of association with quantum field theory, is it that's why the string theory is considered the most promising route to theory of unification or theory of everything?
It is definitely very natural generalization of quantum field theory. It arises very naturally out of it, and quantum field theory by itself is unable to describe the dynamics of gravity, which is why the need was there for a framework which will extend quantum field theory. Quantum field theory is a framework. It's a very powerful, very versatile framework which has described the strong interactions, the weak interactions, and electromagnetism combined into this electroweak interactions. So, and moreover, it describes many other features of complex systems like many body systems, quantum interacting many body systems in materials, in condensed matter physics. They're all captured very well by this framework of quantum field theory. So it's in some sense the best framework we have for describing many body systems or field theories. And uh, string theory kind of enlarges that framework, but at the same time, the surprise is that sometimes string theories are actually dual to quantum field theories also. Sometimes they are equivalent to quantum field theories, but sometimes they are, I mean, but in some ways they are different, but in some ways they are equivalent. It's a very fascinating connection. So yes, string theory and quantum field theory, I think, are very naturally tied to each other, which is one reason to believe that string theory is a good framework
To theory of everything, would
to
you?
at least theory of, I am personally a little allergic to the term theory of everything because it sounds a little too grandiose,
Okay.
uh, it definitely is a versatile framework. String theory is a versatile framework, and it is at least a theory of something, and a lot of things, I think, and whether it will provide a framework for unification of forces and so on remains to be seen.
Okay.
But it definitely, I think, has taught us already a lot of things about quantum field theory as well as general relativity, which we didn't know before. I mean, these are subjects you should realize existed before string theory for decades. They are both about 100 years old, and there were surprising connections between them that string theory predicted, which would not have been otherwise guessed at. And one can actually verify that using nothing but ideas of quantum field theory or general relativity. You can verify many of these predictions independent of whether you believe string theory or not. So string theory has had that power to make at least theoretically very striking predictions.
What are the real world implications, if any, that could emerge from string theory in the future?
I think, of course, it is very difficult to say about any idea in theoretical physics about its direct implication, even when quantum electrodynamics was, or for that matter, even quantum mechanics was uncovered. People thought they were just studying atoms and just understanding things, but now quantum mechanics underlies so much of our technology, or even quantum electrodynamics underlies many things that we use, including lasers and atomic systems, atomic clocks, many objects like that, and so string theory itself, we'll have to see how it will develop. But I think one of the things which it can do is give an alternative framework to quantum field theory, at least applicable in some cases, like I mentioned about the strong interactions, but it could be also to other strongly interacting material systems, like in condensed matter physics. People have tried to use these ideas of this duality between gauge theories and string theories, or quantum field theories and string theories, to understand certain properties of strongly interacting electron systems. So it may very well give you a framework to understand very down-to-earth materials. In fact, already there have been indications due to some work in string theory of um, properties of materials that like simple basic physical properties like their viscosity, and that the viscosity of materials has a certain, maybe a natural limiting kind of values, which wasn't something that people expected earlier. And in fact, it has been a fairly good description of given a fairly good description of something called the quark gluon plasma, an exotic state of matter that is produced when you smash very heavy nuclei together. You produce a plasma of quarks and gluons, which is very strongly interacting and at a high temperature. So the motion of this plasma, it seems to have a very small viscosity, nearing the kind of limiting values that one might expect from general predictions of string theory in certain systems. So I think it's very surprising. There are also ideas in string theory right now connecting quantum gravity to quantum information theory, which underlies our understanding of quantum computation. So quantum information theory in particular is what allows people to study how quantum computers can process information much faster than classical computers, which uses the features of entanglement in quantum mechanics. So there seem to be some new perspectives emerging from quantum gravity, very amazingly, relating geometry to entanglement, and maybe giving again some very crucial insights into quantum information through ideas from quantum gravity. So theoretical physics is very rich and very unified in some ways. So you learn something somewhere, getting solid understanding knowledge somewhere eventually helps you to understand other things. That's been the nature of physics development, and that unpredictability is part of the, I think, the charm of physics, that you're constantly uncovering new connections, new applications, new ways of thinking about things, which is what makes the research fascinating. If we always knew what we are searching for, it would be less rewarding. I feel it's that twists of fate in your journey that I think are the most I think it's the best thing about scientific discovery.
That's great. Let's discuss about learning and understanding string theory for our young audience. So the question is, what mathematical background should a student have to begin working seriously in string theory?
I think if you understand your undergraduate physics, the level of mathematical uh, sophistication and methods that you learn definitely will take you a very long way. You can pick up many other things in geometry, and anyway, when you do quantum field theory, you need to pick up many new ideas of differential geometry and topology. I think one can build on that and learn the additional mathematics as needed. I don't think it is something that's a barrier in itself. I usually physicists just pick up the maths as and when needed. We are, I think, that way very opportunistic.
Okay, let us design a roadmap for an MSc student to learn string theory at the level one needs to start doing research there. Okay, he's just completed his MSc in physics.
So there are some good introductory books which actually even some bachelor students can read. There is a very nicely written book by Barton Zwieback. I think it's called The First Course in String Theory, which is accessible even to undergraduates who have studied a bit of classical mechanics and quantum mechanics as well as electromagnetism. I think sort of a senior undergraduate can read it without learning even very much of quantum field theory. You can actually pick up a good amount of the basics of string theory that way. It's a book with a lot of problems. Problem solving is very important. So I would encourage the student, she or he, to work through problems whenever, whatever subject they're working on. But this particular book is a very good one, I think, to begin to learn things. And then, of course, you should, of course, learn quantum field theory very well. I think that at some point, though, for this book, it's not a prerequisite, the one I mentioned, but eventually you have to learn that very well. And that is a very rewarding but subject which is very subtle and takes some time to understand or internalize. But there are a number of very good books. I think people can begin to learn quantum field theory. I think books by Tony Z and Ryder and so on as introductions, and Peskin and Schroeder and other books for later. Uh, I think there are a number of such very good places to learn and again work through problems. And uh, I think after that, one can probably learn string theory. String theory is a rapidly evolving subject, so many of the books that were written 10 or 15 years ago are probably a little bit dated, though there is a lot of foundational material there, valuable material in there. But I think it's good to read more contemporary reviews by, uh, and that's when I think an advisor is very important, who can point you to the right kind of literature and also what topics to learn in what sequence. So I think it's the initial steps at least people can learn, and then of course you specialize to some areas.
Thank you very much, sir, for it. Why is string theory required to have 9 or 11 dimensions? Why not fewer or more?
Yeah. Uh, so, by the way, I just want to add one more small comment to the previous question, which is there is a wonderful website by the Dutch Nobel Laureate Gerard Toft, which is titled "What Every Theoretical Physicist Should Know," and gives a kind of a very detailed list of topics, resources, books, lecture notes, other things for a theoretical physicist, even at the undergraduate level, to learn and master. And I think that's a very valuable resource for anyone who wants to study theoretical physics in general, very seriously. So, at least at an undergraduate to master's level. So I would recommend that. Many people sometimes write to me asking for this, so I often point them to this resource.
Okay, sir.
Coming to the question on the dimensions, it's string theory in its simplest format is formulated in 10 dimensions, and then there is an M theory, an 11-dimensional version of it. I think that's those are the simplest formulations of string theory, and which may be necessary. Some perhaps is necessary for some features of our real world to be captured, because the extra dimensions give us a lot of flexibility in terms of how or even explanations for why we see certain patterns of particles in the real world. So that was one reason why these extra dimensions were considered. In fact, the extra dimensions were considered even before string theory in the 1920s, 30s, and later what were called Kaluza-Klein theories, as ways in which you could get additional forces together with gravity. And so they were studied independently of string theory, and string theory gives a very natural reason to consider those scenarios. But I must say that right now we understand more of the landscape of string theory, the kind of solutions to string theory that we can have, and that does not necessarily involve 10 or 11 dimensions. There can be solutions of string theory which are consistent, which might have very small number of dimensions, and I think there's a whole range of possibilities which have not been fully explored yet. Uh, so it's so, as I said before, while it is true that the simplest kind of solutions are 10-dimensional, if you want a purely geometric kind of space-time understanding, then in some ways you kind of are 10-dimensional, and that's necessary for the internal consistency of the theory. But the actual condition for that consistency allows for more possibilities than just 10 geometric space-time dimensions. Some of these additional pieces could be something not geometric even. So it's a little difficult to explain, but yeah, so there could be ways, I think, in which you can have even a whole range of other possibilities.
Talking about the conditions under which we can understand the string theory, even in the lower dimensions, like as you just mentioned, it could be even understood in 2 or 3 dimensions also.
Yeah, so string theory admits a large number of solutions, and those there are conditions on the solutions which are a little technical to explain. At the moment, we understand some of those conditions for the consistent string theories. We want these to be sort of solutions in which the string um, can propagate without any sort of inconsistency, and And those conditions are framed. I mean, one of the criteria is some is a number which translates into a dimension in specific cases, but is not always a dimension. It is a measure often of the degrees of freedom that the string can have when it is moving. So that number of degrees of freedom that the string has, or the ways in which it can oscillate, is in some cases related to the dimension, but in all not necessarily in all cases. So, but roughly, if you want, you can think of it as the number of ways in which the string can vibrate. So that number, normally we think of the string can vibrate in all the transverse directions. If a string is moving, it can vibrate in d dimensions. It can if it's moving in d dimensions, there are d-2 transverse directions in some sense. So that's why normally the dimension enters in the consistency of string theory, but there could be other spacetimes in which the number of ways in which it can vibrate is not related directly to the dimension, and so that's why this is only a proxy for the dimension in some cases. I don't know how comprehensible that was, but very roughly, as I said, it's just the number of ways of vibrating of the string.
Okay. What is your response to critiques about string theory's lack of testable predictions and lack of experimental evidences?
Yeah, I think it's easy to criticize. I think it's harder uh, to come up with concrete developments. It is true that physics is at a stage where, or at least the areas of theoretical physics which connect with questions in quantum gravity are more challenging to experimentally test because those regimes are quite removed. And so theory has tried to go ahead without the guidance of experiments, which is always a little risky. It's a little bit going out on a limb, but I think there has been enough of a compelling evidence that there is something very uh, right about string theory, uh, if not for the theory of everything, as I said earlier, maybe theory of something. It is, I think, telling us things about gauge gravity duality, which, as I said earlier, was giving theoretical predictions about quantum field theory and general relativity that both these subjects found very surprising, which was very surprising from the point of view of both these subjects. So if not experimental prediction, it's at least giving theoretical predictions for frameworks which we understand very well, which are experimentally very well tested, like quantum field theory and general relativity are very well tested experimentally, and there are theoretical frameworks, and and string theory is making a connection between them in some circumstances, and that is a very non-trivial achievement, I think, to be able to say something about these very mature subjects. You are predicting a concrete calculation with some numbers, which will have, and the matching of those things is not a coincidence. It's not due to any particular symmetry or anything like that. It's a very non-trivial truth about the theories of the quantum field theories and theories of gravity that there is this connection, and string theory brings it out. So I think there is definitely a case that we have learned a lot of things, if not about quantum gravity per se, about even general relativity and quantum field theory through this process. And I personally am optimistic that this gauge string duality will teach us a lot about why strings arise in nature in many contexts. So that's how I would respond, that it's a very powerful framework which has already taught you a lot of very useful had a lot of very useful theoretical insights, and it has spurred models in many areas of high energy physics, condensed matter physics, and so on, which have been very useful for people's thinking. It has told you things about scattering amplitudes that people measure in colliders, new ways to compute them. All these would not have happened without developments in string theory. So even though they are not connected directly to string theory per se, maybe, but they've been part of the development of string theory has led to all these sort of spin-offs, if you wish. String theory has led to many of these very rich new ideas that people have been using, like I said, even about the quark gluon plasma, about ideas for cosmology, many things. I think it's a rich source of ideas. And when something is a rich source of ideas, you want to explore that. I think that's the human nature, is to go and understand it very well, to go deep into it. And I think that's what people are doing. And I think I'm not saying everyone should do it, but I think a lot of people should explore such ideas.
So you've completed 10 years as the director of ICTS. First of all, congratulations for that. And let
you.
us have a discussion about that role of yours.
Okay, sure. It has been, I think, very fulfilling to be heading this institution for 10 years. I think it has a unique environment which we are trying to create for people to have creative ideas, breakthroughs, and getting young scientists, students, other researchers to also feel that they can think ambitiously to make breakthroughs for science in India. I think we want to make, we say discover in India, not just make in India. We should discover new laws of nature, new ideas of science, and then of course we will have invent in India, make in India will all come, but without that fundamental base of discovery, I think a nation will be always copying things or borrowing things from others. So I feel we need to do that, and ICTS in a small way, we are trying to catalyze something in a bigger system, because ICTS is a small institution, but India has many institutions, but we think of ourselves like a catalyst. A small amount can make a big change through our programs. So the way we do it is through these workshops, schools, collaborative meetings that we organize. In fact, we are not the ones who are organizing it. It is the whole community, scientific community of India, that's organizing it. We facilitate it. So we have people from, in fact, not only Indian institutions, from around the world who put proposals to organize meetings throughout the year. Yeah, so the Indian scientific community puts proposals for organizing programs at ICTS, and we vet them very carefully, meaning actually a national committee of scientists from around India. They look at the proposals carefully and select the ones which are very promising, very exciting. So what we are doing is not as a conference center. We are trying to actually create new collaborations and at the same time train young scientists, younger researchers, PhD students in new areas, which are exciting new frontiers in different areas in mathematics, physics, computer science, biology, climate sciences, many areas which we are now trying to grow in. So that's why we now have about 35 to 40 such workshops every year, and about 3,000 participants. So it is impacting a larger community of people, and a lot of international participants also. So that is making it a very broad activity and giving exposure to our students, and training them through mini courses, which they can then go back and work in new areas. So otherwise, we have to send students abroad for some schools. Here, they all come to ICTS. They work together. They learn together. They build communities that way. So we are trying to build those communities of researchers and create new collaborations. So that's the way in which we hope to catalyze a bigger change in Indian science. Because also an important drawback in Indian scientific ecosystem is that the number of researchers in any institution is very small. It's subcritical.
Yes.
So, but they are scattered all over the country.
Okay.
So, these programs bring people together.
Looking back, what were your biggest goals when you took on this role?
So, my predecessor, Professor Spentawadia, had done a lot of the groundwork in building the campus, which was very important, very beautifully done campus. The last part of the construction work happened in my tenure, but all the plans, everything, it had all been essentially done. And he had also hired some very good young faculty. So one of my immediate goals was to create this as the place where people could organize programs. That was one goal, which I just talked about. Because before that, programs of ICTS were organized by people at different places. And now they had to come here. And so we had to make sure that this is a place where people will want to keep organizing programs. And that demand was there, and it has been growing. The other major challenge was to grow our faculty in new areas and attract the top-notch talent from all over the world. And that I'm very happy has happened. I think we have gotten some of the most excellent talent who have come back as young researchers. And at the same time, we have several senior people, also very distinguished scientists, who have also come here and given their experience, like Professor Deepak Dhar, Professor Ashok Sen, Professor Bala Iyer, many of these people who have contributing a lot to ICTS, Professor Sumati Rao, Professor Venki, many very distinguished scientists at the senior level, as well as young people, young faculty who have joined. So at both levels, I think we have had a good infusion of very good minds, and that has created an intellectual atmosphere here, which I'm very happy about. So one thing I'm also very happy about in the last decade, actually it happened soon after I took over in 2016, was the announcement of the gravitational waves, the first detection of the gravitational waves. And very happy thing for ICTS was that we had a group of 7 people here, Bala Iyer, Ajit, and many students and postdoc who were in the LIGO collaboration, who were part of the discovery paper, and in fact did some very important computations in our computing center, which helped to determine the masses of the black holes, the masses and the angular momenta of the black holes that collided. So that was, I thought, a very good boost for our science in one of the best discoveries of this decade, or maybe even the last 25 years.
What were some of the challenges you encountered, scientific, administrative, or cultural, while this journey of 10 years?
It is always challenging to create an administrative structure that will facilitate the science. I think that is a major challenge. But I think, again, at ICTS, our administrative staff have been remarkably dedicated. Somehow they have felt they are part of a team that is creating a new institution, and so they work very hard outside their office hours and give so much to the institute. And I feel it's very important to keep that morale high for the administration. And so that they are facilitating the research here, and they also feel part of the family.
How do you envision ICT's role in shaping India's future in theoretical and interdisciplinary research?
I think ICTS has a very big role to play, especially through its workshops, but also through the PhD students that we train. We have been training, now we have about 120 PhD students in our graduate program in physics, mathematics, and the physics of life, which is a new interdisciplinary biology and physics program. And that kind of interdisciplinarity that our students are experiencing when they are here in their PhD. I think if they go and then later become faculty members in other institutions, they will carry that culture with them, and it will increase that kind of collaboration and thinking in the Indian scientific ecosystem. So I'm hopeful, I'm quite optimistic about that happening.
So, according to you, is India doing enough to attract and retain top tier researchers, especially in fundamental sciences?
I think we can do better. I think we've had a long history, given how we came as a country out after independence with very meager resources. I think we have set up some very good institutions. I think we can do better in the future years to make it more attractive for people to come back and do science in India. They should feel that these are places that will nurture good science, and that they will not be tied up in administrative kind of tangles, and especially in experimental science where people need good amount of resources, and even in theoretical sciences nowadays people use a lot of computational resources. So resources are very important, and we have to increase the percentage of GDP that we spend even on the existing researchers, and gradually as people get confidence that, oh, good work is coming out of India, it will have a positive feedback. More people will come back. And you see now the situation in the US and other places are not always so easy for getting scientific funding, or for people to do research in a sort of unhindered way. And that is where I think India has a unique opportunity. We have a window where we can attract people back to India and retain them. But we have to have good processes and systems in our institutions.
If our research is correct, you probably wrote an article on why India has not been able to produce Nobel laureates except one or two.
Yes, I felt that I mean, it's a bit of a silly way to phrase it in the sense that Nobel Prizes aren't everything, but it's just a placeholder for global impact. I mean, if not Nobel Prizes, there are many other recognitions globally also, which I think we do not have enough of a share, or if you just measure in terms of impactful ideas. So firstly, I think we should develop more self-confidence. I feel the people who made path-breaking work in the 1920s and 30s, like Ramanujan or Satyen Bose or C.V. Raman or J.C. Bose before that, Saha, all these people were driven by a lot of confidence and feeling that we can also prove ourselves to the world, that we can do wonderful things. I feel we need to regain a little bit of that. But at the same time, the nature of science has also changed from how it was in pre independence. After the Second World War, the US invested in science in a very large way. And since then, in a way, the law of large numbers has come in, which was not there earlier. Earlier, individuals could make a lot of impact, right, even working in a country like India with very few resources. Now resources are the important thing and determine a lot of the breakthroughs, and you need the numbers like I mentioned earlier. We need the So unless you have a large pool of researchers, you cannot just rely on some black swan events, some very rare events. You need to have a systematic way in which people can come up with breakthroughs. So I feel right now we need to do all the things we discussed earlier: attract talent, retain them, provide them institutions where they can think big, ambitious questions. I think all these ingredients are necessary for us to have a global impact in the way I think a country like India deserves to have.
What qualities do you think make for a good researcher in theoretical physics?
Uh, I think very important is mental toughness.
Okay.
I think you have to have stamina, you have to have resilience in the face of failures, you have to have the persistence to pursue ideas, you have to have the self confidence that you can attack problems and make progress in them. If you have a defeatist attitude at the beginning, or you feel I'll only do things which are not risky, then you will only do sort of incremental science. If you want to be doing very breakthrough science, you have to be a little bit bold and even maybe a little reckless.
Okay.
I would say.
That's a new advice.
Of course, you should be very rigorous, and but you should be very bold in your ideas. And it's okay to have a crazy idea. Then you try to refine it. I mean, that should not be the first and last step. It should be the first step, and it should lead to further things. But bold ideas, crazy ideas are important, and I think people should think a little bit like that. But they shouldn't just do it for the sake of crazy ideas. Anyone can have crazy idea, but most of them will be crazy. But you have to see a path, a route, and for that you need persistence, stamina. You need, of course, the rigor, intellectual rigor. So many such qualities, I think. It's not always about smartness. I think smartness is overrated. I keep telling sometimes that you need all these other human qualities which are much more important. And you develop over time a sense of judgment, taste. These qualities also are important, I think, for a researcher.
For students undecided about string theory due to its speculative nature, what advice would you give?
I think string theory is not for everyone. I think everyone shouldn't be thinking about string theory as if you have a certain kind of a taste and maybe even strength in certain things, then by all means, I think explore it. But there are many hundreds of very interesting intellectual questions in physics, in complex systems, in many body systems, in chaos, in fundamentals of quantum information and even quantum mechanics. There are uh, lots of new discoveries in astrophysics and cosmology, gravitational waves, and other things. There are 100 different areas you can explore and new frontiers in biology that physics is being applied to. So people should, I think, align their strengths with their work. So different people have different strengths, and you should see where your strengths can have a big role, can kind of take you ahead. I think it's important to realize that, because you shouldn't be carried away by some hype, either in the plus direction or in the minus direction. You should make your own judgment.
Has your philosophy changed with life as a scientist?
I guess it has evolved. I mean, definitely. I mean, from when you're a school child, as your experience grows,
Right.
you you learn more things, and it has evolved. I won't say it has drastically changed, but it has become more nuanced, more fleshed out, um, more enriched. Yeah.
Okay. What keeps you curious and motivated even after decades of intense research and leadership?
I think curiosity is a very human thing, and I think usually I think circumstances just squash that curiosity. If you feel it's something very precious and you kind of shelter it, you protect it, and then the flame remains alive. I think you have to realize that it's a valuable thing which you need to shield, because there are many things in the world which will try to kind of to dampen that, and you have to keep that flame alive, I think. And Yeah, and then it's enough to sustain you for a lifetime. I think that in a drive to understand more, to learn more, to be fascinated by new things.
That's a profound advice to shield your curiosity. That's great, sir. What legacy or long-term impacts do you wish to leave as both as a scientist and an institution builder?
Well, I mean, I don't know about a legacy, but you create something, that you leave to the future generations, and hopefully, I see myself as a person who is a custodian for some valuable assets for the country and for the world in science. And if I've helped to sort of train some people and impart some of my ideas, that's valuable. But yeah, every generation will take things ahead and build on. So I'm just an inheritor of
What else?
tradition, and I want to just carry it forward, adding something of my own to the future generations.
That's great. Professor Gopakumar, thank you very much for this deeply insightful conversation. Your journey is a testament to how one can blend mathematical elegance with visionary leadership. We wish you continued success in advancing physics and nurturing future generations through ICTS. Thank you very much for this.
Thank you. It has been a pleasure talking with you with your very thoughtful questions.
Thank you very much, sir.